Okay, so I decided to start part two because I only have, again, 30 minutes to record these. That first part was about 23. So I figured I'd break this into two parts, and that was a good breaking point. Um, so the idea here is that the best estimate for instantaneous rate of change is going to happen or occurs when the interval used to calculate average rate of change is made as small as possible. So basically, in order to estimate instantaneous rate of change, what we're doing is we're just picking 2 points that are really, really close together, okay, and doing average rate of change. Okay, so that's the idea. Now, what I'm going to talk about now is I'm going to show you kind of three different strategies that you can use depending on what you're given in a question. Okay, so the first the first type of strategy you would use if you're given a graph. Okay, so for example, I have this graph of a parabola here. Okay, now if we're given a graph and we need to we want to estimate the instantaneous rate of change. So let's say for in this question, we want to figure out what is the instantaneous rate of change when x is equal to 1. Well, what we're going to do is we're going to sketch the tangent line, okay, and then estimate the slope of the tangent line by just picking another point on the tangent line. So here's my where x is equal to 1 on the graph. Now the tangent line here is going to just pass through that point. So I'm going to draw this as best as I can here, right? This is what my tangent line is going to look like. Let's see, I actually might be able to let's see if I can do this here. Shapes. If I can do a line. Oh, it doesn't really let me. Let's see if I can move this. See how good this tool is. No, doesn't really allow. Let's get rid of that. No, I'm going to have to freehand this. Here we go. Let's try this. All right, so I'm just going to draw the tangent line that just touches or just glances over, grazes over the point that's equal to 1. So that's a rough tangent line, okay? It's about the slope at that point. Now, if I want to find the slope of the tangent line, well, I can do a few things. I can just pick another point on this line. So let's pick this one right here because that looks like the coordinate here is 2, 3, and the coordinate here is 1, 1. If I want to determine the slope of this line, I'm going to do y2, x2, x1, y1. So I'm going to do 3 minus 2 over 2 minus 1. That gives me a slope of approximately 1 over 1. Wait, is that correct? 2 minus 1. Oh, no, sorry. 3 minus 1. I was like, that doesn't sound right. That gives me a slope of about 2 over 1, or 2. Okay, so we've made an approximation of the instantaneous rate of change at that point. Okay, so that's your first way. Sketch the tangent line, pick another point on that tangent line, and determine the slope between those 2 points. Okay, the slope between these 2 points. Okay. Another thing you could do, and I'm going to do this in an example below, but let's say you're given a table of values. If you're given a table of values, what you want to do is you want to pick endpoints that are on either side of the coordinate, the tangent, the point that you're looking at, okay, in the table. So let's say, for example, I'm given a table of values x, y, right, let's say I'm given a table of values and it's 0, 2, 4, 6, and my numbers here are 5, 7, 9, 11, right? And I want to make a prediction. I want to figure out what the slope is at x equal to 1. Well, what I'm going to do here is I'm going to use these two coordinates right here because they're on either side of x equal to 1, and I'm going to find the slope between those 2 points there. So in this case, it would be 7 minus 5 over 2 minus 0. That's equal to 2 over 2, which is equal to a slope of 1. Okay, so we're estimating the rate of change there. Okay. The third way, and this is the way that we're going to be focused on in this unit, is by using an equation. Okay, this is going to be our main focus in this unit. And in order to estimate when you're given an equation, what you're going to do is you're going to estimate the slope using a very short interval between the tangent point and a second point found using the equation. So typically what we're going to do, and this is actually, you know what, this is always what we're going to do, is we will choose an interval difference of 0.01. Okay, so what that means is if I want to know the IROC, or the instantaneous rate of change, my pen is coming to, when x is equal to 1, what we're going to do is we're going to figure out what is the corresponding y coordinate when x is equal to 1, and our second coordinate, we're going to use x equal to 1.01 or 0.999. Okay, that's how we're going to estimate the instantaneous rate of change. So we'll look at an example, a specific example here. So example 1. It says a ball is tossed straight up so that the position S in meters at time t in seconds is given by this equation. Estimate the instantaneous velocity of the ball at 3 seconds. Okay? So it's telling us that our t is equal to 3. Okay? We're going to call this t1. That means that t2 is going to be 3.01. Okay? All I do is I'm going to add 0.01. Or if you wanted to, you could do, or your T2 could be 2.99. Okay? That's subtracting 0.01. Either of these numbers are going to work. Totally up to you which one you would like to use. Okay? So what that means is now what I want to do is I want to find my corresponding y values. So I'm going to find what is S of T1 and what is S of T2. Okay. So this is equal to, the first one is equal to 20 bracket 3 minus 5 bracket 3 squared. When I sub that in, I get 15 meters. For T2, I'm going to sub in 3.01, so 20 times 3.01 minus 5 times 3.01 squared. That gives me 14.8995. Now that I know my values, okay, I know my 2 points. So my 2 points now are 315 is my first point, and 3.01, 14.8995 is my other point. And now all I'm going to do is I'm going to find the slope between these two. We can call this x1, y1, x2, y2, and I'm going to use my slope formula. So this is 14, so we'll go 14.8995 minus 15 over 3.01 minus 3, and that's equal to negative 10.05 meters per second. So my instantaneous rate of change at 3 seconds, or my instantaneous velocity is negative 10.05 meters per second. Okay, so I can write that here. The instant, I spelled that wrong. Velocity at 3 seconds is 10 point, and it's going to be negative, which means the ball's coming down. Okay. All right. So again, we're just picking a number. Our second coordinate is just very close to our first coordinate. We're just adding or subtracting 0.01. I just need to get a drink. I'm just going to pause this for just a moment. Okay. So let's take another look at the Donovan Bailey example from yesterday. So in 1997, Donovan Bailey ran the 100-meter sprint in 9.77 seconds. The table below describes his run. One model that describes his run is a quadratic model with an equation of S of t equals 0.28 t squared plus 8t minus 2.454. So that's a quadratic model that approximates or estimates his time distance graph. Okay. The very first question here, A, says estimate Donovan Bailey's instantaneous velocity at t equal to 6 using the table of values. So remember, I'm just going to scroll up. What it said is when we're looking at a table of values, we want to pick endpoints that are on either side of the point that we're looking at. So in this case, we want to estimate it 6 seconds. So what we're going to do is we're going to pick two coordinates, one on either side of 6 seconds. And what we're going to do is we're going to calculate the slope between those 2 points. So we'll go x1, y1, x2, y2. All right. So our slope, or our IROC, instantaneous rate of change, is equal to 60 minus 50 over 6.29 minus 5.44. You can type that into your calculator, and you will get, well, I'll do this, 10 over 0.85, which is equal to 11.76 meters per second. So therefore, his instantaneous velocity at 6 seconds is approximately 11.76 meters per second. Okay, so that's using a table of values. Now, the question in this case also gave us a function, an equation to model his function. Okay, and so we can also use that. So part B says estimate Donovan Bailey's instantaneous velocity at t equal to 6 using the equation. So in this case, what we're going to do is we're going to sub in 6 into our equation, and we're going to pick another t value very, very close to 6 to sub into our equation. So I'm going to sub into my equation t equal to 6. This is going to be my t1. And then I'm going to sub in a number very, very close to 6. So my t2 is going to be 6.01. Now, again, you could use t2. You could do or t2 equals 5.99. Either of those work. I like to typically add 6.01 is a nicer number, I think, than 5.99. So it's totally up to you which one you choose. Okay, my dog is crying. I will be right back. Okay, So we'll sub these values into my equation. I'm just going to write out the equation here. So we're going to say, okay, what is S of 6? We're going to sub 6 into my equation. Well, 0.28 bracket 6 squared plus 8 bracket 6 minus 2.54. I'm going to do the same thing. S of 6.01 equals 0.28 bracket 6.01. So again, noticing that I'm subbing these two coordinates, these two x values, or in this case, t values, into my equation to determine the corresponding y values. Okay. And then I'm going to use those values to calculate my slope or my instant. I keep saying slope, but remember, slope and instantaneous rate of change. Slope and rate of change are the same thing, right? So in this case, if I sub in 6, I get 55.54. So that means my coordinate is 6, 5, 5, 5, 4. So that's my x1, y1. Here I get 55.65. So that means my coordinate is 6.01 and 55.65. So this is my x2 and my y2. And now all I'm going to do is I'm going to calculate. I'm going to do my y2. So my IROC is equal to my y2, 55.65, minus my y1, 55.54, all over 6.01 minus 6, which gives me an answer of 11 meters per second. Okay. Notice our values are not the exact same. Our solutions from A and B are not the exact same. They're relatively close, but again, these are estimates, right? That's the key here. We're not determining the exact rate of change, instantaneous rate of change. We're estimating. Okay. That hopefully made sense. The main idea here is that when you're so again, yesterday, and I'll just do a quick recap. Yesterday, when looking at nonlinear function, right, the idea was we wanted to find the slope or the rate of change between 2 points or of a section. So to find the rate of change of a section of a graph, we draw what's called a secant line. That's a line that goes through 2 points of the graph. We then calculated the slope between those 2 points. Today, we're more focused on a specific point on the graph. We want to know what the slope of a specific point is. So in that case, what we do is we draw what's called a tangent line. A tangent line goes through just 1 point on a graph. In order for us to determine the slope of a tangent line, what we want to do is we want to pick 2 points or a second point that is really, really close to that point on the graph to help us make that prediction. Okay. So if you have any questions, you can email me. I will be back hopefully tomorrow, but I will be back at some point this week. The last thing, and I talked to Miss D'Amato just about the idea of, and I know that some of us, with the last test, the log test, that I'll have those back to you this week when I'm back. The log test maybe didn't go as well as we hoped. So what we are going to do is we are going to allow you to drop your worst test mark in this course. So your lowest test mark will not count towards your final average. Okay, so hopefully that's is some good motivation to be successful on this last one. Again, there's only 2 more lessons in this unit. Okay, this is a very short unit. Our test will likely be Monday or Tuesday. And then that pretty much brings us to our final exam and culminating activities. Okay. We will talk tomorrow. Have a great rest of your day. Your homework questions are here. I also left those with the supply teacher. If you have any questions, send me an email and we'll talk soon. All right. Have a good day.